So we're gonna go over projectile motion, and it's gonna be quite simple. So let's get into it. So oh yeah, we're gonna have a mathematical proof at the end. So that's not simple, but you could skip it if you'd want. I would watch it though if you want to understand it. But when you hit a baseball towards the stand, so let's take a baseball example. We refer to this as a two-dimensional motion called projectile motion because we're measuring motion of a projectile, which is pretty much, isn't that all of classical physics? Um, I don't know. Maybe it's talking about something in the air, which makes sense because it's a projectile. So yeah, I guess so. So like a ball rolling down a ramp in Galileo's case would not be projectile motion. As mentioned in the previous chapter, we separate the ball's motion into x and y components. The x component's initial velocity remains constant because when you hit the ball, like, it's going to go at a constant rate. Nothing is slowing the ball down, except air resistance technically. So when you throw a ball, let's say you throw a ball, but let's say you throw a ball in a vacuum, which means that there's no air molecule slowing it down. When you throw that ball in that thing, the x speed will always be the same. So it will always be traveling forward with the same speed, but the gravity is going to be pulling the ball down. So the only thing determining how far the ball goes is the gravity, because if it hits the ground, that determines where the ball has traveled in terms of the x component. So the x component's emission velocity remains constant, assuming no air resistance. So that means, as we mentioned before, I guess that goes into Newton's laws because there's no motion acting against it. So yeah, the acceleration is zero because the velocity was thrown at the velocity you threw it. It doesn't slow down or speed up. However, due to gravity, the y component changes because the gravitational pull of the Earth is pulling the ball downwards. So here's an example here. It's quite blurry actually, but here let's explain what's happening. So let's rewrite everything down here. So we start at negative 1050 meters. Wait, no, not negative 1050. So let's see what we're given because we're not given the thing. We're only given the acceleration in the y, which is negative 9.80. That's interesting. They put 9.80 when it's 9.81, and they also included the sig fig, so that's kind of strange, but it's okay. We'll go with it. 9.8 meters slash second squared. The Vy should be the V, that's so blurry, but the Vy should be 0 because you're not thrusting the ball downwards. You're just gonna drop it. And the V0 x, is that an x? It's quite blurry. Oh no, it's the initial velocity. Wait. Oh no, Vy is okay. So we have Vy and V0. That's all we're given pretty much at 0 meters per second. So what is, and we're given that the velocity in the x direction is 115 meters per second. And note that it doesn't change here because no one's like thrusting the ball forward, or there's no one like hitting the ball while it's dropping, so it's not speeding up or slowing down while it's in the air in the x direction. So if we have 115 meters per second, first we have to calculate the time. So we're given that this y is negative 1050. So this plane is 1000 negative 1050 or 1050 meters in the air. But we want to calculate how long it'll take for it to hit the ground. So 10 negative 50 meters. So if we denote this as 0 meters in the air, which it's not, or 0 meters, that means when it drops 1050 meters, the final y, which we'll write as yf, will be negative 10,050 meters. So let's plug that into our kinematic equation. So this will tell us how long it'll take for the ball to hit the ground. So ay, so the initial velocity in the y direction will be 0 meters per second, because we're just simply dropping it. We're not thrusting it down with any force. So it'll be 0 because vt plus 1 half at squared, and it will be a negative because it's dropping right there, and we denoted that falling downwards is negative, and gravity is a force that pulls things down, so it's also negative here because we denoted it like that. So that's the logic there. That's kind of hard to understand if you don't take physics. I mean, if you haven't done physics before, but If you denote falling as negative, then this is also negative. So, as we know, it's t squared divided by 2. We can do some pretty simple math here to get negative 4.9. So t is equal to 1050 divided by 4.9 square roots. And that's going to give us 14.6 seconds. So it's going to take 14.6 seconds for this thing to fall to the ground, which I'm not sure why they gave us the x component, but maybe they wanted us to calculate how far the ball was traveling, and simply we'll just use the v, or we'll use the position, which is x equals vxt, because we're assuming no acceleration in the x direction, which is simply just 115 times 14.6, and I'm not going to do the math in my head because it's too complicated. It's going to give us 1679. So it traveled 1679 meters right, and it took 14.6 seconds for it to hit the ground. So gravity. Although the acceleration in x direction doesn't have a constant force like gravity, the gravity or acceleration in the y direction definitely affects how the projectile goes. So, like, go back to a baseball example here. Let's throw a baseball towards the crowd. Let's say this is the bleachers here and there's people here. I don't know. This ball's motion, if we put it on a graph, probably looks something like this. But the x speed never changes. That means from here to here, the x gap is going to be this. The slope is, I mean, not the slope. The ball is going to be moving at the same speed from here to here as here to here. And it will be moving at the same speed from here to here. So, in short, the x direction never changes. But the y direction is getting pulled down because of, I guess, gravity. So, although the gravity never affects how fast this ball is moving towards the x direction, it tells the ball when it stops, because that's when it hits the ground, because the gravity has pulled the ball to the ground. So that's the example that I go in here. For example, if we had a plane, or if we had the projectile thing, because the plane dropped the care package, which was the example in the previous thing, and there was no gravity, and we just pushed this ball, it would go forward infinitely because the gravity would never pull the box down. So projectiles have symmetry in time, and speed, meaning that the uptime is the same as the downtime. So to explain this in a parabolic motion, take that same ball, and let's say this is the vertex, which is the maximum point here. The time it takes for it to travel upwards is the same as the time for it to travel downwards. So downwards, upwards. This is the same exact thing. So imagine throw a ball straight upwards. At first it goes upwards, so let's throw this ball upwards, and let's say it travels 5 meters. So it's right here. And then we say it travels, downwards 5 meters to the original position. It's going to take the same amount of time to travel upwards, and then it's going to take to travel downwards. So if we say that we threw the ball upwards at 20 meters per second, the gravity changes the velocity at the same rate. So gravity is 9.8 meters, but we'll denote it as 10 meters /seconds squared for simplicity. So if it's traveling 20 meters per second upwards, after 2 seconds, the ball will stop, because now there's no more, after 2 seconds, the ball will stop because gravity lowered this by 10 meters per second at 1 second. So it's going to be 10 meters per second, and at the second gravity is going to completely halt the ball. So it would stop after 2 seconds. So it will be at 0 meters per second upwards. Now starting from 0, which is the ball right here, starting from 0 meters per second, the gravity is going to pull the ball down at 10 negative meters per second at 1 second, and then negative 20 meters per second at the second one. So the velocity, the acceleration is changing the velocity at the same rate, regardless of up and down. So that's the symmetry. The peak before and after the vertex will always be the same. So let's come over here. This is the proof here. Vertical motion, ignore air. So this is the kinematic equation. And we have this proof here. So let's go over this proof here. And this is the one given in our book. Oh wow. It's kind of invisible, so let me just screenshot it. So we start with this equation, which everyone knows. Perhaps the best kinematic equation that I like to say. So we have this equation, which is just dealing with kinematics in the y direction. But as we know, the initial velocity, the initial y is we're gonna denote as 0. So we can just factor a t out, or so then it would just become negative gt over 2 squared plus VOY t, because we just took this out because we denoted it as 0, and 0 plus something doesn't do anything. We'll factor a t out, giving us negative. The way they wrote it was in the opposite direction, so VOY minus gt over 2, which is equal to 0 because we're seeing when it falls back to the original position. So that means t has to equal 0, or t equals 2 VOY over g, which is just simply solved using the zero product rule. You can look that up in mathematics. The same reason why quadratics have 2 solutions. So the time total, it can't be 0 because when you throw the ball up and it comes back down, it could be 0 if you never threw it, but we're assuming that we threw the ball upwards. So this answer has to be the right one because that's actually a number instead of 0. And you know you can't get a ball up and down in 0 seconds because that means nothing has happened. So it's time in apex, which I don't even know what that means, like time in apex. That's what it says. So at the top, Vy is going to be equal 0 because if we throw the ball upwards, it's going to be 0 right here at the peak. And VOY minus GT is going to be 0. Same thing as what it says here. So the time up is going to be half. Or it has to be 0 because it'll be 0 right there. And it goes back to the VF equals VOY plus AT. And then since gravity is a downwards force, it'll be VOY minus GT. So the simple kinematic equation. So that's half, and the time down equals the total time minus up, because because if we plus both sides here, the total time is going to be the time up plus time down. So it's going to be 2 VOY g minus VOY g equals VOY g equals t up. In simple terms, the time it takes for something to go up is going to be the same as the time it takes for something to go down, regardless of initial velocity, which is really genius, actually. So whoever figured that out is a genius. So, yeah.